Welcome back to the Deep Dive. Today, we're not just looking at small tweaks or incremental improvements. We're really plunging into a solution that tackles one of machine learning's big headaches in industry: surface defect detection.
Right.
For anyone who's wrestled with deploying vision systems out there, think pharmaceuticals, automotive, aerospace, the absolute need for perfection. It's paramount. A tiny flaw, even microscopic, can mean huge costs, safety risks, potentially even recalls. And historically, we've kind of swung between two extremes.
Yeah,
right?
that's a good way to put it.
Either painstakingly labeling thousands of defects by hand,
Yeah.
or hoping a model just magically spots something it's never seen. It's this tension that's really defined the field.
That frames it perfectly. This whole area, accurately and quickly finding surface imperfections, it's historically been, well, conservative, very labor-intensive, lots of human visual inspection. But like you said, with the incredible leaps in deep learning recently, these automated systems are just fundamentally changing the landscape. We're shifting from subjective, error-prone manual checks to real-time, precise localization of defects and anomalies. This is really where the academic research hits the road, meeting practical industrial needs, promising not just efficiency, but better quality control, often better safety too.
Absolutely. And that brings us right to today's deep dive, a truly groundbreaking paper. It's titled "No Label Left Behind: A Unified Surface Defect Detection Model for All Supervision Regimes." This comes from Blaž, Rolih, Matic, Fučka, and Danijel, Skočaj at the University of Ljubljana. Our mission today is really to explore how their work, specifically with their model, SuperSimpleNet, is setting a completely new standard. Adaptability, performance in a really tough field.
Yeah, and the core problem they tackle so well is this disconnect we often see between how data actually looks in real manufacturing settings, the different annotation scenarios, and what existing models can handle. Think about the spectrum, right? You've got totally unsupervised settings, maybe only normal samples, then weakly supervised, just image-level label saying defect, yes, no.
Right, no location.
Exactly. Then mixed supervision, some pixel detail, some just image labels, and finally, fully supervised, everything meticulously masked out.
The ideal but expensive case.
Precisely. And traditional models, they're often stuck in just one or maybe two of these regimes. That fragmentation, it leads to inefficiency. You might discard valuable data just because the labels aren't perfect.
Or if I had to train completely different models.
Right. SuperSimpleNet, as you said, tackles this head on. It proposes one single, highly efficient, and remarkably adaptable discriminative model.
And the promise sounds huge. Unification, top performance, and serious speed. They position SuperSimpleNet as the very first model that can fully leverage all that available data across all four scenarios. Is that really a paradigm shift, or more like a brilliant combination of existing ideas?
Well, it's a bit of both, but I'd lean heavily towards paradigm shift. For our listeners who've been in the anomaly detection trenches, unifying this is a massive challenge. It really boils down to the fundamental tension between learning these sharp decision boundaries you get in supervised learning versus modeling the normal distribution in unsupervised methods.
Totally different philosophies.
Exactly. They've often felt almost mutually exclusive. Models good at one often fail spectacularly at the other. The insight here is realizing that all labels, even the partial ones, have value. They contain signal.
Don't throw anything away.
Right. SuperSimpleNet's breakthrough is in its architecture and learning procedure that doesn't just jam paradigms together, but intelligently orchestrates their strengths. It can learn robustly from a few pixel-level labels while also benefiting from loads of unlabeled normal data and those sparse image-level flags.
Okay, so how does it do that? What are the key innovations?
To give a quick preview, they introduce a novel synthetic anomaly generation process. We'll definitely dig into that. There's an enhanced classification head and a significantly improved learning procedure overall.
And it works in practice.
That's the crucial part. They don't just promise it, they rigorously show state-of-the-art results on 4 tough benchmark data sets. And critical for industry, it clocks in under 10 milliseconds inference time. We'll definitely unpack each of those claims as we go.
Okay, so we've set the stage, what it is, why it's important, but let's circle back to that fragmentation you mentioned. If unifying this is so critical, why has it taken so long? Why hasn't a solution like SuperSimpleNet emerged before? What were the roadblocks?
That's a really good question. Historically, the community kind of split into two camps. Academic research often simplified defect detection into two main, somewhat separate problems. First, there's surface defect detection, or SDD. This basically assumes you have both normal and defective images during training. It frames it as a standard supervised learning task. And performance is generally great if you have enough well-labeled data. Think pixel-perfect masks for cracks on an airplane wing, super accurate, but incredibly expensive and time-consuming to create. The second main path was unsupervised anomaly detection, or UAD. This is what you use when you only have normal surface images for training.
Which is common, right? Normal samples are usually easy to get.
Exactly. Anomalies are rare, often unseen during training. UAD lets you spot these novel defect types. Generative models, reconstruction methods, density estimation, those have been the tools here.
But there's a trade-off.
Always. SDD struggles with anything new, anything it wasn't explicitly trained on. UAD might catch novelties, but often lacks the precision of supervised methods when labels are available. Bridging them often involve complex heuristics or lots of domain-specific tuning. Never really a single model that could just adapt seamlessly.
That split really highlights the core difficulty. So let's break down the specific trade-offs for our listeners. Why do these two approaches, robust in their own ways, often fall short in real industrial settings?
Yeah.
What are their weak spots?
Okay, let's look at the specific limitations. For supervised methods, STD, yes, they perform well on known defects, but fundamentally they learn a decision boundary based only on the training data.
So they're biased towards what they've seen.
Precisely. This makes them inherently prone to missing novel defects. A new type of scratch, a subtle discoloration not in the training set. A supervised model might just ignore it completely.
In the labeling.
Oh, the labeling. Pixel-level annotation is tedious, labor-intensive, incredibly expensive. It can disrupt production lines, and often you just can't get enough diverse defect samples for every possible defect type. It's a huge practical barrier.
Okay, so that's STD. What about UAD?
Now, unsupervised methods, UAD, tackle that labeling problem head-on by training only on normal samples, so they can detect novel anomalies, which is a massive advantage when you don't know what might go wrong next. But they generally perform worse than supervised methods when you do have comparable labeled data. And critically, they can't leverage any anomalous samples that you might have, even if they only have simple image-level labels.
So potentially valuable information gets ignored.
Exactly. It's effectively discarded. So neither extreme, purely unsupervised, or fully supervised is really optimal for the messy reality of detecting diverse defects on surfaces where your data annotation is often a mix.
Right. Neither extreme is perfect. It really feels like being stuck between a rock and a hard place. So the core argument from the authors is, to get the best results, you have to use all the labels you have, no matter how detailed they are.
That's the essence of it.
Which brings us right back to needing a unified model. And that's where Super SimpleNet comes in.
Okay, let's dive into Super SimpleNet itself now. The paper claims it handles this wide spectrum of data and supervision. How does it actually manage that flexibility without becoming, overly complicated or unstable? It's built on the foundation of SimpleNet, which was already quite effective, but the authors made some really significant enhancements to both the architecture and the learning process to achieve this adaptability.
Okay.
It's specifically designed to utilize all the kinds of training data you might encounter. That means, first, just normal images, which are usually plentiful. Second, anomalous images where you only have an image-level label just knowing something is wrong, but not where.
The weak label.
Right. And third, fully annotated images with those precise pixel-level segmentation masks showing exactly where the anomalies are.
The strong labels.
Exactly. And based on these inputs, Super SimpleNet operates across 4 distinct training regimes, which they nicely show in Figure 1 of the paper.
Can you walk us through those again?
Sure. You have unsupervised, only normal images used, classic anomaly detection, then weakly supervised, normal images plus those anomalous images with just the image-level flags, then fully supervised, where all images, normal and anomalous, have pixel-level annotations.
The gold standard data scenario.
Right. And finally, what's often very practical, mixed supervision. Here, all images have image-level labels, but only a subset also gets the detailed pixel-level masks.
That sounds much more like real-world data collection.
It absolutely is. This flexibility is a huge differentiator because it directly mirrors the often messy reality of data availability in many industrial settings.
That flexibility is really compelling. But from an engineering standpoint, what were the key innovations, the sort of core scientific contributions that actually allowed them to pull this off and bridge these different supervision types?
They highlight 3 main scientific contributions that really work together. First, and probably the most fundamental for its broad use, is an improved synthetic anomaly generation process.
Okay, generating fake defects.
Essentially, yes, but it's not just random noise. It's a novel, quite clever approach that significantly boosts training in unsupervised settings, but it also helps training effectively even when you have limited or no pixel-level labels in the other modes. It's really key for building the model's segmentation ability without explicit ground truth.
Interesting. What's the second contribution?
Second, they designed a very effective classification head. It's simple architecturally, but powerful. It excels at capturing global image context and making really good use of those image-level annotations. Its simplicity is actually key to its adaptability, helps avoid overfitting across the different supervision levels.
And the third?
Third, and maybe most encompassing, is that Super SimpleNet truly represents a unified model for all supervision paradigms. It's about integrating techniques and insights from all these different levels of supervision into one single cohesive architecture.
So it's not just bolting things together.
Not at all. It's an intelligent orchestration that promotes knowledge transfer between the regimes. This enhances the overall performance significantly, rather than just having separate solutions cobbled together.
You mentioned Table 1 in the paper gives a good visual summary of this unification. Could you walk us through that for our listeners? How does it stack up against other state-of-the-art methods?
Absolutely. Table 1 is quite insightful. It compares Super SimpleNet directly against 12 other well-known methods in defect and anomaly detection names, like SDNet, TNet, DRA, DRIM, and others.
Okay.
The table lays out 4 critical requirements for each method. Can it process normal images only? Can it handle anomalous images with just image-level labels? Can it handle anomalous images with pixel-level labels? And crucially, does it meet that practical industry need for inference speed under 10 milliseconds?
And the result?
The result is striking. Only Super SimpleNet ticks all 4 boxes.
Really? None of the others manage all 4?
Nope. Many methods might handle normal images and pixel labels, for instance, but they stumble on the image level only labels. They often just can't use that information. Others might handle different label types, but are way too slow for real-time inspection on a production line.
I see.
So this table really drives home that Super SimpleNet is unique in its comprehensive ability to handle all common types of input data and supervision levels, while also being extremely efficient. It really highlights that unified design philosophy, keeping real-world deployment constraints in mind.
That's a very clear advantage. Okay, let's zoom into the architecture now.
Yep.
Figure 2 lays it out. For our technical listeners, can you trace the journey of an image as it goes through the Super SimpleNet pipeline? Maybe walk us through each module.
Sure. Let's follow an input image, call it I. First stop, the feature extractor. They use a standard pre-trained convolutional network, specifically WideResNet 50, pre-trained on ImageNet. It pulls out features, fellow, from a couple of its layers 2 and 3 in their setup. These are rich, high-level features.
On a standard backbone.
Right. Next, they tackle a common issue with ResNet-type networks. The deeper features have lower spatial resolution, which can make it hard to spot small defects. So, they have an upscaling module.
How does it work?
An upscaling layer simply doubles the feature resolution. Equation 1 in the paper shows the detail. This makes sure all the feature maps from different layers have the same spatial size before they get concatenated together, that's equation 2, to produce an intermediate map, F.
Got it. Matching resolutions.
Exactly. Then, following the SimpleNet design, they apply local average pooling with a 3x3 kernel, equation 3. This step is important because it allows each feature location to encode information from its neighborhood, capturing more context. This produces the final feature map, F, where each location is enriched with local patterns, crucial for recognizing subtle defect textures.
Okay, upscaling and context. What's next?
After upscaling, we hit the feature adapter. Now, features from ImageNet pre-training usually transfer well, but a simple linear layer here adapts these features specifically for the segmentation head's task. This adapted feature is called A in Figure 2.
Only for the segmentation head. Why?
The idea, or hypothesis, is that this lets the segmentation and classification heads operate in slightly different latent spaces. The segmentation head gets features fine-tuned for pixel-level prediction, A, while the classification head works with the more general, globally informed S features. This separation might help each head specialize better without interference.
Interesting specialization. And then
comes that really innovative part, the latent space masked anomaly generation. This only happens during training. It's where synthetic anomalies get intelligently injected into both the segmentation features, A, and the detection features, F. This is absolutely key to making it work across all supervision regimes.
We definitely need to unpack that more later. What happens after the anomalies are injected?
The now potentially perturbed features go into the segmentation and detection module. This has that dual branch design we'll look at closely. And finally, for inference when you're actually using the model, all that training machinery, the synthetic anomaly stuff, is completely bypassed.
For speed.
Exactly. This allows the network to directly and very quickly predict the anomaly map, MOMOR, and the image level score S. That's fundamental to achieving that sub 10 meters speed.
Okay, that latent space masked anomaly generation definitely sounds like a cornerstone. You said it effectively creates its own training data, even when labels are missing. How does that actually work? Figure 3 illustrates it, but what's the mechanism? Why is it so effective across different scenarios?
Right. This is where it gets really clever. And yes, it's kind of like the model teaching itself by creating challenges. It's a major contribution. The core idea is generating synthetic anomalies using Gaussian noise, but here's the kicker. The noise is applied only within specific regions defined by a synthetic anomaly mask, MSynth.
Okay, not just random noise everywhere. How is the mask created?
They start by generating Perlin noise. For listeners maybe less familiar, Perlin noise creates these natural-looking pseudo-random patterns, clouds or marble textures, much more coherent than just static.
More realistic than pure noise.
Exactly. That spatial coherence is important because real defects often have some shape or texture, not just random speckles. They generate this Perlin noise and threshold it to create an initial mask, MP.
Okay, so that defines potential anomaly shapes. What's next?
Now this is crucial. For the final synthetic mask, MSynth, they remove any regions that correspond to actual known anomalies from the ground truth mask MP. Equation 4 shows this simply. MemSynth MP 1 mon dt.
Why remove the real anomaly areas?
Because you don't want to overwrite or corrupt the valuable information from a real labeled defect by plastering synthetic noise on top of it. You want to preserve that ground truth signal.
Makes sense. What if there is no ground truth mask? Like in unsupervised or weakly supervised?
Good point. In those cases, MT is effectively empty, so the Perlin mask MP just becomes the synthetic mask MSynth. Synthetic anomalies can then be generated anywhere on the feature map.
Okay, so you have the mask MSynth, then you apply the noise.
Precisely. Gaussian noise, sampled from a normal distribution, is restricted just to those MSynth regions. This noise OIN is then added to both the F and A feature maps, creating the perturbed versions PF and PA.
And the benefits of doing it this way?
Several key benefits. 1, it creates more realistic, spatially coherent synthetic anomalies within the feature space. 2, because they are masked and somewhat randomized, it prevents the model from overfitting to unrealistic patterns, which is especially important when you don't have many or any real anomaly examples. 3, it stabilizes training by showing the model a wider variety of plausible anomalies in each batch. They also retain the feature duplication trick from SimpleNet, applying noise to both original and duplicated features, which adds further stability.
And how does this affect the training targets?
The final anomaly mask M used for the segmentation loss includes both the synthetic anomalies and any real ones. And the image level anomaly label Y for the classification loss is set to 1 if any anomaly, synthetic or real, is present, otherwise it's 0. This provides a really rich training signal across all the supervision modes.
That latent space generation is definitely clever. Okay, so once you have these potentially perturbed features, PF and PA, where do they go? Let's follow them into that segmentation detection module shown in Figure 4. How do the two heads, especially that new classification head, work together to give both precise localization and robust detection?
Right. This dual branch design is really central to how Super SimpleNet works, embodying that no label left behind idea. First, you have the segmentation head, DSeg. This part is largely kept from the original SimpleNet. Its job is to generate that pixel-level anomaly map, Mo.
That's the localization part.
Exactly. It assigns an anomaly score to each pixel, pinpointing where defects might be. This is where the fine-grained spatial understanding happens.
Okay, and the other branch?
The other branch is the classification head, DCLs. This is a new addition and really key to Super SimpleNet's discriminative power and adaptability. Architecturally, it's kept quite simple. Just a 5x5 convolutional block, then some pooling layers, and a final fully connected layer.
Simple but effective.
That seems to be the case. Despite its simplicity, it provides strong discriminative power. It's designed to capture more global image context, which helps reduce false positives and improves detection of subtle defects that might be missed by focusing only locally.
How do these two heads interact then? It's not just two separate paths, right?
No, they interact cleverly. The anomaly map MO coming out of the segmentation head is actually concatenated with the main feature map F, or the perturbed PF, during training. This combined feature tensor then goes into the classification head's convolutional block.
So the classification head sees both the original features and the segmentation head's output. Why?
The thinking is that MO provides fine-grained, pixel-level evidence of anomalies to the classification head. Even if there's no pixel-level ground truth, MGT, for a particular sample, MO, which has been trained using those synthetic anomalies, still offers valuable spatial hints. It lets the classification branch leverage the spatial understanding developing in the segmentation branch, enriching its global decision about whether an anomaly is present anywhere.
I see. It gets spatial clues even without explicit labels. And the final output.
The output from the classification head's convolutional block and the anomaly map MO itself are pooled, concatenated one more time, and then passed through that final fully connected layer. This produces the single image level anomaly score, indicating the overall likelihood of a defect in the image.
And the benefit of this dual branch design.
It's efficient, it prevents overfitting because of the simple classification head, and it's explicitly designed for mixed supervision. It allows the model to naturally leverage different kinds of labels by having these distinct but interacting mechanisms for localization, deseg, and overall detection, DCLs.
That ability to train with mixed supervision is really a cornerstone. How is the learning procedure itself set up to handle this flexibility? Accommodating different levels of labels without messing things up seems like a tricky balancing act.
It absolutely is, and the learning procedure is quite ingeniously designed to manage it. Let's start with the segmentation loss, LSEG. They use a truncated L1 loss, shown in equation 5.
L1, okay, why truncated?
L1 is generally more robust to outliers than L2, good for noisy defect boundaries. The truncation at a threshold 0.5 is the key nuance. It means that once the error for a pixel prediction gets beyond that threshold, the penalty doesn't increase as sharply.
What does that achieve?
It encourages a softer decision boundary. It tells the model, essentially, focus on getting reasonably close. Don't obsess about absolute perfection on potentially ambiguous boundary pixels, because that can lead to overfitting. It's a practical choice for better generalization, especially with subtle or fuzzy defects.
Makes sense. And that's combined with focal loss?
Yes, it's combined with focal loss, alpha LAFE, as shown in equation 6. Focal loss is crucial here because defect detection data is almost always highly unbalanced. Way more normal pixels than defect pixels. Focal loss helps the model focus more on the hard-to-classify examples, the actual defects, rather than being overwhelmed by the easy normal background.
Okay, so that's the segmentation loss. What about the classification loss?
For the classification loss, LCLs, they also use focal loss, alpha Kasalowi 7, for the same reason, handling the imbalance between normal and anomalous images at the image level.
Now, how are these combined?
The final combined loss, L, is a weighted sum of LSEG and LCLs, controlled by this really important dynamic term, gamma, shown in equation 8.
Gamma, how does that work?
This O term, defined in equation 9, is the magic behind the mixed supervision. It acts like a switch. Ga is set to 1 if the image is normal, or if it's anomalous, it has a full pixel-level label. MGT is available. In these cases, both the segmentation and classification heads are trained using their respective losses.
Okay, and when is gamma 0?
Alsace is set to 0 if the image is anomalous. BUT only has a weak image level label, no MGT. In this situation, the segmentation head's loss, LSEG, is effectively turned off for that specific sample because there's no ground truth to compare against. However, the classification head's loss, LCLs, is always active for anomalous samples.
Ah, I see. So the segmentation head only trains on samples where it has ground truth, real or synthetic VM. But the classification head trains on all anomalous samples using the image level label.
Exactly. The impact is huge. It allows the segmentation head to still learn effectively, even if many samples lack pixel labels, thanks to the synthetic anomalies providing a target M. And it ensures the classification head always benefits from knowing an image is anomalous, even if the exact location isn't specified in the label. It truly leaves no label behind.
And there was one more detail about weighting the segmentation loss.
Yes. Following an approach from SegDecNet, they apply weights derived from a distance transform on the ground truth mask, MGT, when available, to the LSEG calculation.
Distance transform, what does that do?
It's a classic technique. It calculates, for each pixel inside the anomaly mask, its distance to the nearest boundary pixel. By weighting the loss this way, you give more importance to the pixels deep inside the anomaly, where the annotation is usually certain, and less importance to the pixels right on the boundary, which are often ambiguous or noisy.
So it focuses learning on the core of the defect.
Precisely. It's a smart way to handle the inherent uncertainty in manual annotations, making the segmentation learning more robust. And just to recap the targets, the mask M for LSEG includes both synthetic and real anomalies, and the label Y for LCLs is 1 if any anomaly is present, 0 otherwise. During inference, remember, the anomaly generation is off, and the model predicts MO and S. MO is then typically upscaled and maybe smoothed with a Gaussian filter to match the input image size for visualization.
Okay, architecture and training makes sense. Let's move to the validation. How did they test SuperSimpleNet? What datasets were used across these different supervision settings, and what metrics did they use to evaluate it?
They used a comprehensive set of 4 challenging datasets, chosen specifically to cover the full range of supervision modes and typical industrial challenges. For fully mixed and weakly supervised settings, they relied on 2 real-world datasets, Sensum SODF and KSDD2.
Talk about those.
Sensum SODF has images of things like pharmaceutical soft gels and capsules, with both normal examples and precisely annotated defects. It's interesting because pharma defects can be quite subtle. They used 3-fold cross-validation there. KSDD2 has images of various production items where defects often look very similar to normal regions, making it notoriously difficult. It uses standard train test splits. Figure 5 in the paper gives some good visual examples from KSDD2.
Okay, and for the unsupervised setting?
For the unsupervised setting, they went with the big benchmarks. MBTech AD and Visa. These are widely considered the gold standards for UAD.
What makes them gold standards?
It's not just the number of categories. MBTech has 15, Visa has 12, but the sheer diversity and subtlety of the anomalies across different textures and objects. Things like scratches, contamination, structural defects. Many are really hard for even humans to spot consistently. Both datasets follow the standard UAD protocol. Train only on normal images, then test on a mix of normal and anomalous images. Figure 10 shows some examples.
Got it. And the metrics used for evaluation?
They used standard, well-established metrics appropriate for each dataset and task, ensuring fair comparison. For image-level performance, did it detect an anomaly in the image? They used area under the receiver operator curve, or AUROC, for Sensum SODF, MBTech AD, and Visa. For KSDD2, which focuses a bit more on detection precision against a balanced set, they used average precision, APDET.
And for localization, how well did it pinpoint the defect?
For pixel-level performance, they used area under the per-region overlap, or AUPRO. For Sensum SODF, MBTech AD, and Visa, AUPRO is good at handling multiple defect regions. For KSDD2, they used average precision for localization, or APLOC. These choices align with how these datasets are typically evaluated in the literature.
Any key implementation details worth noting?
Yeah, a few things. They used the AtomW optimizer, ran for 300 epochs, batch size 32, noting larger batches helped because they generate more varied synthetic anomalies per batch. Specific learning rates for different parts, a scheduler, gradient clipping for stability. The Gaussian noise for synthetic anomalies was N00.015. Interestingly, the Perlin noise threshold varied, 0.6 for mixed fully supervised, maybe focusing anomalies near normality boundaries, 0.2 for weakly unsupervised on MVTech AD, and 0.6 for Visa. Perhaps broader anomalies help more when pixel labels are absent. Standard image net normalization, resizing per dataset rules, flipping augmentation in supervised modes. They balanced epochs with equal normal anomalous samples for stability. And all results are averaged over 5 runs with different random seeds, giving robust mean and standard deviation numbers.
All right, let's get to the results, the core performance, starting with fully supervised setting, the best case scenario with full labels. How did SuperSimpleNet stack up against the state-of-the-art?
In the fully supervised setting, SuperSimpleNet really delivered. It achieved state-of-the-art results, as shown clearly in Table 2. On Sensum SODF, it hit a mean detection AUROC of 98.0%.
How does that compare?
That's a solid 1.1 percentage point improvement over the previous best, TriNet. Doesn't sound huge, but it represents a 35.5% reduction in error rate. That's significant in high-stakes applications like pharma.
Okay, and on KSDD2?
On KSDD2, it got a state-of-the-art detection APED of 97.8%. That's 1.6 percentage points better than the prior best, cutting the error rate by 42%. Also important. The results showed greater stability, lower standard deviations compared to the original SimpleNet, which is vital for reliable deployment.
Any thoughts on why it performed so well here?
The authors hypothesize it's primarily down to that simple but effective classification head. By capturing more global information efficiently, it seems better able to make that final distinction between normal and anomalous, even subtle ones. And the qualitative results in Figure 5 back this up. You see cleaner anomaly maps, less noise, more accurate scores compared to others.
A very strong start. But, like we said, The real challenge often lies in the weakly supervised setting, with only image-level labels. This is where many models falter, especially on localization. How did SuperSimpleNet handle this?
You're right, this is a tough test. And SuperSimpleNet performed remarkably well here, according to Table 3. In the weakly supervised setting on Sensum SODF, it achieved a detection AUROC of 97.4%.
How close is that to its fully supervised result?
Get this, it's only zero point 0.6 percentage points lower than its fully supervised performance on the same dataset. It shows incredible resilience to the lack of pixel labels. For comparison, the best-related method, TriNet, dropped by 5.4 percentage points when moving from fully to weakly supervised. That's a huge difference.
Wow. And localization, could it still find the defects?
Impressively, yes. It obtained 92.8% AUPRO for localization on Sensum SODF. Many methods don't even report localization in this setting because it's so hard without pixel ground truth. On KSDD2, it also showed strong results, 97.2% APDET and 47.6% APPLOC.
And the drop from fully supervised was small there, too.
Again, minimal. Just a 0.6 percentage point reduction in APDET compared to its fully supervised performance. Contrast that with big drops for other methods like SegDecNet down 22.1 points or MammaNet down 16.2 points.
So what's the key to this weak supervision robustness?
The authors attribute it directly to that novel synthetic anomaly generation. It effectively creates plausible targets for the segmentation head to learn from, even when real ground truth masks are missing. It bridges that information gap, drastically reducing the need for expensive pixel-level annotation for achieving good performance.
Okay, now on to the mixed supervision scenario. This seems like the sweet spot for practicality. Some detailed labels, some weak ones. How does SuperSimpleNet handle this blend? Can it gracefully use whatever labels are available?
The mixed supervision results, which you can see in Figures 6 and 7 and Appendix A, really highlight the paper's main point. SuperSimpleNet shows significantly less dependence on having all samples pixel labeled. It performs better than competitors, even when only a fraction of the anomalous samples have detailed masks.
Better how?
Get this. On Sensum SODF, SuperSimpleNet, running in its weakly supervised mode, no pixel labels at all, actually outperforms the fully supervised performance of the prior state-of-the-art method, TriNet.
Seriously, that's a big deal for reducing annotation effort.
Absolutely. It means you can potentially get state-of-the-art results with vastly less labeling cost and effort. On KSDD2, it consistently beats related methods in detection, even if all samples are only weakly labeled. While another method, DSR, sometimes edges it out slightly in localization in specific mixed settings, SuperSimpleNet's localization clearly improves as you add more pixel-level labels. Figure 8 shows this scaling. And importantly, its image-level anomaly scores remain accurate even without any pixel labels, thanks to that effective classification head.
That really drives home the value of mixed supervision as a strategy. Okay, last setting. Purely unsupervised? No anomaly examples during training at all? How does it fare against the UAD specialists?
Even in the purely unsupervised setting, SuperSimpleNet achieves state-of-the-art performance. Table 4 shows it hitting 98.3% EROC on MVTech AD and 93.6% AROC on BISA.
Better than the original SimpleNet, too.
Yes, notably better in anomaly detection and with more stable results, lower variance across runs. The qualitative examples in Figure 10 are also telling. SuperSimpleNet tends to produce more accurate anomaly scores and cleaner anomaly maps. The high-certainty defect areas seem better separated from background noise, which would make interpretation easier for a human operator.
And the success here again comes down to
the improved synthetic anomaly generation. It allows the model to effectively simulate and learn from a diverse range of potential anomalies, even when it has never seen a real one during training. It's powerful enough to drive state-of-the-art UAD performance within this unified framework.
Okay, accuracy across all regimes is impressive. But for industry, speed is king. Production lines don't wait. How fast is SuperSimpleNet? What's the computational cost?
This is another area where it really shines, making it highly practical. Figure 9 and Table 9 provide the numbers. It achieves an average inference time of just 9.5 milliseconds per image.
Wow, under 10 meters. What does that mean in terms of throughput?
That translates to processing 262 images per second on an NVIDIA Tesla V100S GPU. That's fast, really fast.
And compared to other methods?
Critically, the paper confirms it's the fastest method identified that works effectively across both unsupervised and supervised settings. Many specialized models are slower or only work in one regime. This combination of versatility and speed is a major selling point for deployment.
Does it handle higher resolution images efficiently too? Sometimes you need more pixels for small defects.
It does scale reasonably well. For instance, processing a larger 1024 by 1 in 24 images, it still manages 21 images per second, using about 1.5 gigabytes of GPU memory. There are diminishing returns. Doubling resolution doesn't double performance, but having the flexibility to go to higher resolutions when needed, while still being efficient, is a significant plus. This blend of top accuracy and speed is what makes it potentially transformative for real-time quality control.
To really isolate the impact of each innovation, the authors did an ablation study taking components out or changing them. What did this reveal about why Super Simple Net works so well? What happens when you remove parts?
The ablation study, detailed in Table 5, is super insightful. It really validates their design choices. Let's go through some key ones.
Okay, what about the upscaling module?
Removing it, SSNO upscale, hurt both detection, down 0.7 AUROC points, and localization, down 1.4 AUPRO points. This shows it's important for accurately handling spatial details, especially for smaller anomalies that might get lost otherwise.
The classification head.
Removing it, SS there, no CLS, drops supervised detection by 1.0 point, as you'd expect less discriminative power. Interestingly, it slightly improved unsupervised detection by 0.1. The authors think maybe the classification head, when trained only on synthetic data in the unsupervised case, might slightly overfit to those synthetics, so removing it helps a tiny bit there.
What about making the classification head more complex?
Bad idea, apparently.
Right.
Using a complex head, SSN complex CLS, didn't help supervised detection at all, and it hurt unsupervised detection by 2.6 points. This strongly suggests the simplicity of their classification head is key. It's powerful enough but avoids overfitting, especially to the synthetic data used across different modes.
And the input to that classification head, you mentioned it uses the anomaly map MO.
Yes, and removing MO as input, SSNCL's no MO, had a massive negative impact in the unsupervised setting of 46.0 point drop. In supervised settings, the drop was small, 1.4 points. This clearly shows MO is vital for guiding the classification head when only synthetic anomalies are present, preventing it from going completely off the rails. Using the adapted features A instead of F, SSNCL's WADAPT, also slightly hurt performance, suggesting the unadapted F features are better for the global classification task. Other quick takeaways. The improved training setup, loss function, scheduler, etc., SSNOL train, made a noticeable difference. 1.6 points detection, 3.6 localization, highlighting the importance of stable optimization. Generating synthetic anomalies only on non-anomalous regions, SS overlap versus the default, was slightly better, confirming you shouldn't corrupt real defect signals. The segmentation loss weighting improved things, 0.4 detection, 1.9 localization, by handling boundary ambiguity well.
What about comparing their anomaly generation to the original SimpleNet?
Replacing their mask generation with SimpleNet's original method of perturbing the whole feature map, SSNSN anom, caused a significant drop, especially in unsupervised, down 4.4 points. It shows their new method is better suited to the dual-head architecture. And finally, even in supervised settings, adding synthetic anomalies, SSNO anom versus default, still helped slightly, 0.3 detection, 2.5 localization, showing they act as a useful regularizer even when real labels are present. And of course, they are absolutely essential for unsupervised and weakly supervised learning.
That's a really thorough justification of their design choices. Okay, moving beyond just industrial defects, how well does this approach generalize? Did they test it elsewhere? And what limitations do the authors acknowledge?
It shows good signs of generalization. Table 7 shows it performing well in the medical domain using the BMAD benchmark for unsupervised anomaly detection. This involved complex images like histopathology slides and brain MRIs. Finding anomalies there successfully suggests the core principles aren't just limited to industrial surfaces.
That's promising. What about image resolution and failure modes?
The image resolution study, tables 8-9, confirmed higher resolutions like 512 by 512 help detect smaller anomalies on datasets like Visa, and the model scales reasonably well computationally. The misclassification analysis, table 10, figure 11, was interesting. False positives were pretty rare and often happened on images with ambiguous minor imperfections, highlighting real-world labeling challenges. Notably, synthetic anomalies actually reduced false positives by 21-33%, acting like a regularizer.
And false negatives, missed defects.
False negatives were mostly extremely small defects, 1% image area. This points to the limitation of feature resolution. Tiny things get lost. Higher input resolution helps mitigate this. Synthetic anomalies also give a modest reduction in false negatives. The label ablation study, Figure 12, beautifully showed how performance climbs consistently as you add more informative labels from just normal, unsupervised, to adding image level weekly, to adding some pixel level mixed. It works well with limited data, but clearly benefits from more. And the backbone ablation, Table 6, confirmed WidersNet 50 was a good choice for balancing performance and efficiency.
So what are the acknowledged limitations?
They identify a few key ones. First, dependence on the pre-trained feature extractor. If the ImageNet features don't capture what's normal for a very different domain, performance will suffer. Second, while generally robust, some specific real-world cases might need hyperparameter tuning. And third, as mentioned, detecting very tiny anomalies really benefits from, or might require, higher resolution inputs, which has computational trade-offs. These are clear directions for future work.
Okay, let's wrap this up and bring it all together. After this deep dive, what stands out to you as the single most important takeaway from the Super SimpleNet paper? For researchers, for practitioners?
I think the core achievement is crystal clear. Super SimpleNet is demonstrably the first unified model that doesn't just work, but excels across that entire spectrum: unsupervised, weakly supervised, mixed, and fully supervised. And it does this with state-of-the-art accuracy and that crucial sub-10 millisecond speed. It genuinely leverages all the available data, bridging those historical divides and anomaly detection through its clever architecture and learning strategy.
So what? What does this mean for machine learning, data science, and especially for those industrial applications going forward? What should our listeners be thinking about?
Well, this work strongly suggests that for optimal, practical anomaly detection, you really should use all the information you have, whatever its form. It powerfully demonstrates the benefit of combining insights from both unsupervised and supervised worlds, closing that gap we talked about.
Right.
And it really elevates mixed supervision, not just as a compromise, but as a highly effective strategy balancing performance and annotation cost. This points towards future research focusing on these hybrid approaches, intelligently blending different data signals. For deployment, it offers concrete strategies for dealing with the messy, incomplete data common in manufacturing, potentially lowering barriers to adopting sophisticated defect detection.
This has been a fascinating look at how clever architecture, innovative synthetic data use, and smart learning can tackle a really tough, persistent industrial problem. As we think about the implications of no label left behind, here's a final thought for you to consider. What new frontiers in quality control might this kind of unification unlock? And how could it fundamentally reshape how we even approach data collection and annotation in these complex, constantly changing industrial systems?